Hello, and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here isn't just about stars, it's about the stories they hold, the myths whispered by ancient astronomers, and the quiet mysteries still waiting. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. The universe is expanding, not metaphorically, not poetically, but literally, in the most precise sense physics can offer. Every galaxy beyond our local neighborhood is moving away from us, carried not by engines or momentum, but by the stretching of space itself. The fabric of the cosmos is growing, swelling, unfolding like a vast invisible tide that has been rising for nearly 14 billion years. When you first hear this, it sounds impossible. Space does not feel like it is stretching. You cannot sense it in your room, cannot measure it with a ruler across your desk. The expansion happens on scales so large that entire galaxies serve as markers. Their distance is growing not because they travel through space, but because space itself is expanding between them. Imagine a balloon with dots drawn on its surface. As you inflate it, every dot moves away from every other dot. None of them sits at the center. That is the reality we inhabit, though our balloon has more dimensions and no surface we can see from outside. For most of human history, the idea would have been unthinkable. The stars appeared fixed, eternal, pinned against the dome of night. Constellations rose and set in predictable patterns. The heavens felt stable, unchanging, a cosmic clock that ticked but never shifted. Even when Copernicus suggested that Earth moved around the sun, the notion felt absurd. How could we be in motion if we felt nothing? The discovery of expansion overturned all of that. It revealed that the universe is not a stage on which events unfold, but a participant in the drama. Space itself has a history. It was once smaller, denser, hotter. It cooled and stretched, giving room for stars and galaxies to form. And it continues to grow, carrying those galaxies apart, driving them into isolation across voids too vast to cross. To look up at the night sky is to see this motion frozen in light. The photons reaching your eyes tonight left their galaxies millions or billions of years ago, traveling across a cosmos that was stretching all the while. Their wavelengths have been pulled longer by the expansion, shifted toward the red end of the spectrum. This red shift is the signature of a universe in motion, a fingerprint left by the growth of space. The impossibility of it is what makes it astonishing. We live inside something that refuses to stand still. The ground beneath our feet feels solid, but the cosmos around us is restless. Galaxies slide away in all directions, not fleeing from us specifically, but from one another. Every observer in every galaxy sees the same pattern. The universe expands everywhere at once, with no center and no edge. What makes this discovery even more remarkable is that it was not predicted. No ancient philosopher imagined that space could stretch. No medieval scholar dreamed that the stars were receding. The idea emerged only when astronomers turned powerful telescopes toward faint smudges in the sky and measured their light with exquisite care. The data forced the conclusion. The universe is not eternal and unchanging. It is dynamic, evolving, still unfolding from an ancient beginning. The first is that we are small, living on a pale planet, orbiting an ordinary star in one galaxy among billions. The second is that we are capable of understanding the largest scales imaginable of tracing the history of the cosmos back to its origin and forward to its fate. The expansion of the universe is both humbling and exhilarating, a reminder that reality is stranger and grander than our everyday experience suggests. As you let this thought settle, picture the galaxies around you. They are not stationary. They are drifting, carried by the silent growth of space. The distances between them are increasing, not because they move through the void, but because the void itself is growing. This is not motion in the ordinary sense. It is the stretching of the stage on which all motion occurs. The impossible has become real. The universe expands, and we are here to witness it. High above the smog and lights of Los Angeles, perched on Mount Wilson in the San Gabriel Mountains, sits an observatory that changed our understanding of everything. The air there is thin and clear, the nights dark and steady, perfect for peering into the farthest reaches of space. In the 1920s, this remote outpost housed the most powerful telescope in the world, the 100-inch Hooker telescope, a marvel of engineering and ambition. It was here that Edwin Hubble, a young astronomer with a methodical mind and a quiet determination, began his work. Hubble was not the first to wonder about the faint smudges of light scattered across the sky. For centuries, astronomers had catalogued these nebulae, as they were called, without knowing what they truly were. Some believed they were clouds of gas within our own Milky Way. Others suspected they might be something more distant, more extraordinary. Hubble set out to find the answer. Night after night, he trained the great telescope on these nebulae, photographing them with long exposures, studying their light with patient care. What he found would rewrite the map of the cosmos. Within some of the nebulae, Hubble was able to resolve individual stars. Among them were Cepheid, variables, stars that pulsate with a regular rhythm, brightening and dimming in cycles that can last days or weeks. The period of their pulsation is tied to their true brightness, which means they can be used as cosmic yardsticks. By comparing how bright they appeared with how bright they truly were, Hubble could calculate their distance. The results were staggering. These stars were far too distant to belong to the Milky Way. The nebulae they inhabited were not nearby clouds, but entire galaxies, each containing billions of stars, scattered across unimaginable distances. What people had thought was the whole universe, the Milky Way and its surroundings, was suddenly revealed to be just one galaxy among many. The night Hubble made this discovery, the universe grew larger, not physically, but in the human mind. Our galaxy, which had seemed so vast, so central, was reduced to one island in an ocean of islands. The cosmos stretched beyond what anyone had imagined, filled with galaxies, extending in all directions, each as rich and complex as our own. But Hubble did not stop there. As he continued his observations, measuring the distances to more and more galaxies, he began to notice something strange. The light from these galaxies was shifted toward the red end of the spectrum. This red shift was a sign of motion, a Doppler effect caused by galaxies receding from us. The farther away a galaxy was, the more its light was shifted, the faster it appeared to be moving. When Hubble plotted the data, distance against velocity, he found a simple, linear relationship. The farther away a galaxy was, the faster it receded. This became known as Hubble's law, and it revealed something profound. The universe was not static. It was expanding. The mountaintop where this discovery was made is still there, though the observatory now shares the sky with satellites and aircraft. The 100-inch telescope still points upward, though newer instruments have surpassed it. But the spirit of that place, the quiet dedication of looking deeper and farther, remains. It was a place where patience and precision converged, where the largest questions could be asked and answered, Mount Wilson was more than a location. It was a vantage point, both physical and intellectual. From that height, above the haze of everyday concerns, the cosmos revealed itself. The galaxies were not fixed. They were moving, receding, carried by the expansion of space itself. The universe had a history, and it was still unfolding. To imagine Hubble at work is to picture long nights in the cold, the great telescope swinging slowly to track the stars, photographic plates exposed for hours to capture the faintest light. It was tedious work, demanding patience and care, but it was also profoundly human. A solitary figure gazing into the depths of space, seeking to understand what lay beyond. The discovery made at Mount Wilson did not come with fanfare. Hubble published his results in scientific journals, presented them at conferences. The response was gradual, as scientists absorbed the implications. But over time, the idea took hold. The universe was not what they had thought. It was larger, older, more dynamic. And it all began on that mountaintop, under the clear, dark skies of California. As you think of that place, picture the observatory dome opening, the telescope pointing upward, the stars scattered like dust across the void. Somewhere in that vastness, galaxies were receding, their light stretched by the expansion of space. And on that mountain, one man was patient enough to notice. The light from distant galaxies carries more than just photons. It carries information, a story written in wavelengths and intensities, a message encoded in the spectrum. When Edwin Hubble first examined the light from galaxies beyond the Milky Way, he expected to see familiar patterns, the bright and dark lines that mark the presence of hydrogen, helium, and other elements. What he saw, instead, was something subtle but profound. The lines were there, but they were shifted, not by much, but enough to notice. The familiar pattern of hydrogen, normally found in specific parts of the spectrum, had been pulled toward the red end. This red shift was not random. It followed a pattern. The more distant a galaxy, the more its light was shifted. At first, this might seem like a technical detail, a minor quirk of observation, but Hubble understood what it meant. The red shift was a Doppler effect, the same phenomenon that causes an ambulance siren to drop in pitch as it drives away. When a source of light moves away from you, its waves are stretched, increasing their wavelength and shifting the light toward red. Not just that galaxies were moving, which in itself was remarkable, but that they were all moving away. No matter which direction Hubble looked, the galaxies showed red shifts. It was as if the entire cosmos was fleeing from us, as if we stood at the center of some great cosmic repulsion. But that could not be right. The idea that we occupied a special position in the universe had already been overturned. Copernicus had shown that Earth was not the center of the solar system. Later discoveries revealed that the Sun was not the center of the galaxy. The principle of mediocrity, the idea that our location is not privileged, had become a cornerstone of cosmology. The answer was subtle. The recession was not because galaxies were fleeing from us specifically, but because space itself was expanding. Every galaxy, no matter where it was located, would see the same pattern. If you lived in a galaxy billions of light years away, you would observe the Milky Way and every other galaxy receding from you. The expansion was universal, not centered on any one point. To grasp this required a shift in perspective. It meant thinking of space not as a static backdrop, but as a dynamic entity, something that could grow and stretch. The galaxies were not moving through space in the ordinary sense. They were being carried by the expansion of space itself. This idea was strange, almost counterintuitive. How could space expand? What did that even mean? If the universe was growing, what was it growing into? These questions had no easy answers. They pushed at the edges of what language and intuition could handle. But the data were clear. The red shifts were real, the pattern was consistent, and the simplest explanation was expansion. The spark of mystery was not just in the observation, but in what it implied. If the universe was expanding now, then it must have been smaller in the past. If you reversed the motion, running the cosmic film backward, galaxies would come closer and closer together, their distances shrinking, their densities increasing. Eventually, they would merge into a single, incredibly hot, incredibly dense state. The universe had a beginning. This was revolutionary. For centuries, people had assumed the universe was eternal, without start or end. The idea of a cosmic origin, a moment when everything came into being, had been the domain of theology and myth. Now it was suggested by science, implied by the redshifts of galaxies and the mathematics of expansion. The mystery deepened. If the universe began, what caused it to begin? What existed before? And what lay ahead? Would the expansion continue forever? Or would it one day halt and reverse, pulling the galaxies back together in a cosmic collapse? The spark of mystery ignited 1,000 questions, each more profound than the last. Hubble himself did not immediately leap to these conclusions. He was cautious, methodical, focused on the data. He measured distances, recorded redshifts, plotted graphs. But others, including theorists like Georges Lemaitre, recognized the implications. Lemaitre proposed that the universe had expanded from a primeval atom, a tiny seed of matter and energy that exploded outward in what would later be called the Big Bang. The spark of mystery was this, that a simple observation, the redshift of galactic light, could lead to such grand conclusions. It connected the act of looking through a telescope to the origin and fate of everything. It turned astronomy into cosmology, the study not just of stars and galaxies, but of the universe as a whole. As you consider this, picture the moment Hubble first saw the redshifts. The photographic plate developed, the lines of hydrogen visible but shifted. A small anomaly, easy to overlook, but in that shift lay the story of expansion, the history of the cosmos. When Edwin Hubble presented his findings to the scientific community, the reaction was not immediate acceptance. It was caution, skepticism, and in some cases, outright disbelief. The universe was expanding was so foreign to the prevailing worldview that many scientists struggled to accept it, even when confronted with the data. For centuries, the universe had been thought of as eternal and unchanging. Philosophers and astronomers alike assumed that the stars, the galaxies, even space itself, had always existed and would continue to exist forever. The notion of a dynamic cosmos, one that had a history and was still evolving, clashed with this deeply held assumption. Some scientists questioned the measurements. Were the redshifts really evidence of motion, or could they be caused by something else? Perhaps light lost energy as it travelled across vast distances, producing a redshift without any actual recession. This idea, known as the tired light hypothesis, was proposed as an alternative. Others wondered if the redshifts might be gravitational, caused by light climbing out of deep gravitational wells. But as more data accumulated, these alternative explanations fell away. The redshifts were consistent, the pattern clear. The tired light hypothesis could not account for the linear relationship between distance and velocity. Gravitational redshifts could not explain why all galaxies, regardless of their mass or location, showed the same pattern. The simplest explanation, and the one supported by Einstein's equations, was that space itself was expanding. Even Einstein, whose theory of general relativity predicted that the universe could expand or contract, had initially resisted the idea. When he first derived his equations, they suggested a dynamic cosmos. But Einstein found this so unsettling that he added a term, the cosmological constant, to force the universe into a static state. He believed the cosmos must be eternal and unchanging, and he altered his mathematics to make it so. When Hubble's observations showed that the universe was indeed expanding, Einstein reportedly called the cosmological constant his greatest blunder. He had the tools to predict expansion, but he had let his philosophical assumptions override the mathematics. It was a humbling moment, a reminder that even the greatest minds can be blinded by preconceptions. For others, the discovery sparked awe. The idea that the universe had a beginning, that it was still growing, that space itself was dynamic, opened new vistas of thought. It connected cosmology to thermodynamics, to quantum mechanics, to the deepest questions of existence. If the universe began, then time itself began. If space was expanding, then the very fabric of reality was in motion. Georges Lemaitre, the Belgian priest and physicist who had independently proposed the idea of an expanding universe, saw the discovery as a confirmation of his primeval atom hypothesis. He imagined the universe emerging from a single point, a cosmic egg that hatched and spread outward. For Lemaitre, this was not just science but theology, a vision of creation that bridged faith and reason. Others were less comfortable. Some saw the idea of a cosmic beginning as too close to religious doctrine, as if science were being bent to fit a biblical narrative. They preferred models that avoided a definite origin, such as the steady-state theory, which proposed that the universe was eternal but constantly creating new matter to maintain a constant density as it expanded. This model would later be disproven, but for a time it offered a way to preserve the idea of an eternal cosmos. The reaction to Hubble's discovery was therefore mixed. Awe and disbelief walked side by side. For some, the expanding universe was a revelation, a glimpse into the true nature of reality. For others, it was a challenge, a disruption of cherished beliefs. But as the evidence mounted, as more galaxies were measured and more redshifts recorded, the disbelief faded. The universe was expanding, whether we liked it or not. What made the discovery so powerful was that it came not from theory but from observation. It was not a philosophical argument or a mathematical speculation. It was data, hard and undeniable. The galaxies were receding. The light was shifted. The cosmos was in motion. No amount of wishful thinking could change that. The awe came from the realization of what this meant. We lived in a universe with a history, a universe that was still becoming. The stars were not eternal fixtures, but temporary phenomena, born from cooling gas and destined to fade. The galaxies were not static islands, but travelers, carried by the stretching of space. Everything we saw was part of a grand unfolding, a process that began nearly 14 billion years ago and would continue for trillions more. To stand under the night sky with this knowledge is to feel both small and connected. Small because the cosmos is so vast, so old, so indifferent to human concerns. Connected because we are part of it, made of the same elements, governed by the same laws, participants in the same story. The awe is in the scale, the disbelief in the strangeness. Both are responses to a truth too large to fully grasp. As you rest now, imagine the scientists of the 1920s gathered in lecture halls, poring over data. Picture the moment when disbelief gave way to acceptance, when the expanding universe became not a theory but a fact. That moment changed everything. The discovery that the universe is expanding raised a question so fundamental that it still echoes through cosmology today. If space is stretching, if galaxies are receding in all directions, then where is the center? Where is the point from which everything is moving away? The instinct is to imagine a center. We are used to explosions, to fireworks scattering outward from a single point. We think of expansion as motion through space, with fragments flying away from an origin. But the expansion of the universe is not like that. There is no center, there is no edge, there is no point from which the galaxies are fleeing. This is where science and mystery collide. The data are clear, the redshifts are real, the expansion is measured and confirmed, but the explanation defies our intuition. How can something expand without a center? How can space stretch without stretching into something else? The answer lies in thinking of space itself as the thing that expands. The galaxies are not moving through space. They are being carried by the stretching of space. It is not an explosion in the ordinary sense, but a growth of the fabric itself. Every point in space sees the same pattern of recession. Every observer, no matter where they are, sees galaxies moving away. There is no privileged position, no central hub. To visualize this, astronomers often use the analogy of a balloon. Imagine dots drawn on the surface of a balloon. As you inflate it, every dot moves away from every other dot. None of them is at the center, because the center is not on the surface. The surface itself is expanding, and every point on it is equivalent. The universe is like that surface, except in 3 dimensions instead of 2. This analogy helps, but it also confuses. The balloon expands into the surrounding air, but the universe does not expand into anything. There is no outside, no external space into which the cosmos grows. The expansion is intrinsic, a property of space itself. To ask what lies beyond the universe is to ask a question that may not have an answer, like asking what is north of the North Pole. This is where mystery enters. Science can describe the expansion, can measure its rate, can predict its consequences, but science struggles to explain what expansion truly means in a way that satisfies our everyday intuition. We are left with equations and analogies, tools that work but do not fully resolve the strangeness. The paradox deepens when we consider the implications. If the universe has no center and no edge, then every location is equally valid. Our position in the cosmos is not special. The view from the Milky Way is the same, in principle, as the view from any other galaxy. This principle, known as the cosmological principle, is a cornerstone of modern cosmology. It says that on large scales, the universe is homogeneous and isotropic, the same everywhere and in every direction. But how do we know this is true? We can only observe our local patch of the universe, the region within our cosmic horizon. Beyond that, we cannot see. So, the cosmological principle is an assumption, a reasonable one based on the uniformity we observe, but still an assumption. It is possible, though unlikely, that the universe beyond our horizon is very different. This tension between what we know and what we assume is where science meets mystery. We have data, we have theories, we have models that fit the observations beautifully. But we also have gaps, regions of uncertainty where the equations cannot take us. The expansion of the universe is one of those places where the solid ground of science gives way to speculation. Some physicists have proposed that the universe might have a shape, a global geometry that wraps back on itself. If space is curved in the right way, you could travel in a straight line and eventually return to your starting point, like circling the Earth. In such a universe, there would be no edge, but also no infinite extent. It would be finite but unbounded, a cosmic sphere or torus. Current measurements suggest that space is flat, or very nearly so, which implies it may be infinite. But even this is not certain. The measurements have margins of error, and the universe could have a slight curvature that we have not yet detected. The question remains open, hovering between science and mystery. What makes this so compelling is that it connects to the deepest questions we can ask. What is space? What is the universe? Is it finite or infinite? Does it have a beginning and an end? Or is it eternal in some sense? These are not just scientific questions, they are philosophical ones, touching on the nature of existence itself. The expansion of the universe forces us to confront these questions. It reveals that the cosmos is not a static container, but a dynamic entity, something that grows and changes. It shows us that space and time are not absolute, but relative, woven together into a fabric that can stretch and curve. And it reminds us that our knowledge is always partial, always limited by what we can observe and measure. As you let this thought settle, imagine the universe as a vast tapestry, threads woven together, stretching outward in all directions. There is no center to the weaving, no edge where the threads end. It extends as far as we can see, and perhaps far beyond. The mystery is not in the pattern, but in what the pattern means, in what it tells us about the nature of reality. When the evidence for an expanding universe became clear, the scientific community did not speak with one voice. Different minds, shaped by different philosophies and assumptions, interpreted the data in different ways. Some embraced the idea of a dynamic cosmos, while others resisted it. The result was a division, not of enemies, but of perspectives, each offering a different vision of what the universe might be. On one side were those who accepted the implications of Hubble's observations and Einstein's equations. They saw the red shifts as evidence of expansion, the expansion as evidence of a beginning. Georges Lemaitre, the Belgian physicist and Catholic priest, proposed that the universe had emerged from what he called a primeval atom, a single point of unimaginable density and energy. This idea, later refined and renamed the Big Bang, suggested that the cosmos had a history, a moment of origin from which everything unfolded. Lemaitre's vision was both scientific and theological. He saw no conflict between his faith and his physics. For him, the expanding universe was a revelation, a glimpse into the mechanics of creation. The equations spoke of a beginning, and that beginning resonated with the idea of a creator. But Lemaitre was careful to separate his religious beliefs from his scientific work. He presented his primeval atom hypothesis as a natural consequence of the data, not as a proof of God. On the other side were those who found the idea of a cosmic beginning uncomfortable. Fred Hoyle, a British astronomer, was among the most vocal skeptics. Hoyle believed that the universe was eternal, without beginning or end. He could accept that the universe was expanding, but he rejected the notion that it had started from a singular point. To reconcile these ideas, Hoyle and his colleagues developed the steady-state theory. The steady-state model proposed that the universe was indeed expanding, but that it maintained a constant density by continuously creating new matter. As galaxies moved apart, new matter appeared in the gaps, forming new galaxies over time. In this view, the universe had no origin. It had always existed and would always exist, a cosmos in perpetual balance, expanding but never changing in its overall character. Hoyle's resistance to the Big Bang was partly philosophical. He disliked the idea of a beginning because it seemed to invoke something beyond physics, a first cause that smacked of theology. Ironically, It was Hoyle who coined the term Big Bang, using it dismissively during a radio broadcast to describe Lemaitre's hypothesis. The name stuck, though not in the way Hoyle intended. The debate between these camps was not just about data, but about worldview. Those who supported the Big Bang saw it as a triumph of observation over assumption, a willingness to let the universe reveal itself, even if the revelation was strange. Those who supported the steady state saw it as a defense of reason, a refusal to abandon the principle of an eternal cosmos without overwhelming evidence. For years, the two theories coexisted, each with its proponents, each with its explanatory power. The steady state could account for the expansion without requiring a beginning. The Big Bang could account for the redshifts and the observed uniformity of the cosmos. But as new observations came in, the balance began to shift. One of the decisive blows to the steady-state theory came in 1965, when Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs, detected a faint, uniform glow of microwave radiation coming from all directions in the sky. This cosmic microwave background, as it came to be known, was the afterglow of the Big Bang, the cooled remnant of the intense heat that filled the early universe. The steady-state theory had no explanation for it, while the Big Bang predicted it precisely. With the discovery of the cosmic microwave background, the debate effectively ended. The steady-state theory faded from prominence, and the Big Bang became the accepted framework for understanding the universe's history. But the division of minds during those years was not without value. It forced scientists to test their assumptions, to refine their models, to look for new evidence. The tension between competing ideas drove cosmology forward. What this division reveals is that science is not a monolith. It is a conversation, a process of debate and refinement. Different minds bring different perspectives, and those perspectives shape how we interpret the data. The expansion of the universe was a fact, but what it meant, what it implied, was open to interpretation. The Big Bang and the steady state were two different stories told about the same observations, and only time and evidence could decide which was true. Even today, divisions persist. While the Big Bang is widely accepted, questions remain about the details. What caused the expansion to begin? What happened in the first moments, before the universe cooled enough for matter to form? Is the Big Bang itself the ultimate origin, or was there something before it? These questions divide cosmologists, not into opposing camps, but into different schools of thought, each exploring different possibilities. The minds that divided over the expanding universe were united by a common goal: to understand the cosmos. They disagreed on the interpretation, but they shared the same commitment to evidence, to mathematics, to the pursuit of truth. Their debates enriched the field, sharpened the questions, and ultimately brought us closer to understanding. As you let this thought rest, imagine those scientists, Lemaitre and Hoyle, standing on opposite sides of a great question. One saw a beginning, the other saw eternity. Both were brilliant, both were sincere, and both, in their own way, were right to push the boundaries of what was known. Once the expansion of the universe was established as fact, the next question became urgent. How fast is it expanding? What is the rate at which space stretches, carrying galaxies apart? This question was not merely academic. The answer would determine the age of the universe, its size, and ultimately its fate. The pursuit of this number, known as the Hubble constant, became one of the central quests of 20th century cosmology. It required measuring two things with exquisite precision: the distances to galaxies and the velocities at which they recede. Velocities came from redshifts, which were relatively straightforward to observe. Distances, however, were far more challenging. To measure how far away a galaxy lies, astronomers had to build what is often called the cosmic distance ladder. Each rung of this ladder relies on a different method, and together they stretch from the nearest stars to the farthest galaxies. At the bottom are parallax measurements, where the apparent shift of a nearby star against the background as Earth orbits the Sun reveals its distance. This method works well for stars within a few thousand light years. From there, astronomers move to standard candles, objects whose intrinsic brightness is known. Cepheid variable stars are among the most important. Their pulsation period is tied to their luminosity, so by measuring how bright they appear, astronomers can calculate how far away they are. Edwin Hubble used cepheids to measure distances to nearby galaxies, opening the door to the larger cosmos. For even greater distances, astronomers turned to Type Ia supernovae, exploding stars that shine with nearly uniform brightness. These stellar detonations can be seen across billions of light years, making them ideal markers for the most distant reaches of the observable universe. By comparing their apparent brightness with their known luminosity, distances could be inferred. Each step of the ladder introduced uncertainties. How well did we understand the intrinsic brightness of cepheids? Were there subtle variations in supernovae that we were missing? Small errors at one rung could cascade upward, magnifying as distances increased. The pursuit of the Hubble constant was therefore a pursuit of precision, a careful refinement of methods and measurements. In the decades following Hubble's initial work, different teams of astronomers arrived at different values for the expansion rate. Some measurements suggested the universe was expanding quickly, implying a young cosmos. Others suggested a slower expansion, implying greater age. The discrepancies were troubling. They hinted at systematic errors, unknown factors that skewed the results. One of the most ambitious efforts to resolve these discrepancies came with the launch of the Hubble Space Telescope in 1990. Named in honor of Edwin Hubble, the telescope was designed to observe the universe free from the blurring effects of Earth's atmosphere. One of its key missions was to measure Cepheid variables in distant galaxies with unprecedented accuracy. Over the course of years, the Hubble Space Telescope observed dozens of galaxies, identifying hundreds of cepheids, measuring their periods and brightnesses. The data were painstaking, but the result was a major step forward. The Hubble constant was refined to within a few percent, giving cosmologists a clearer picture of the universe's expansion rate. But the pursuit did not end there. As measurements improved, a new puzzle emerged. Different methods of measuring the Hubble constant began to yield slightly different results. When astronomers used the distance ladder, parallax, cepheids, supernovae, they arrived at a value around 73 kilometers per second per megaparsec. But when they used observations of the cosmic microwave background, the faint afterglow of the Big Bang, combined with cosmological models, they found a lower value, around 67. This discrepancy, known as the Hubble tension, has persisted despite increasingly precise measurements on both sides. It may point to new physics, perhaps related to dark energy or dark matter, or it may reveal unknown systematics in the data, subtle errors that have not yet been identified. Either way, it has become one of the hottest topics in modern cosmology. The pursuit of the Hubble constant is more than a technical exercise. It is a window into the fundamental workings of the universe. The rate of expansion determines how long the cosmos has been growing, how large the observable universe is, and what the future holds. A faster expansion means a younger universe. A slower one means greater age. The number connects the present to the past and the future. There is something deeply human about this pursuit. It is the desire to measure, to quantify, to pin down a number that describes reality, but it is also an acknowledgement of humility. The universe does not make itself easy to measure. Distances are vast. Light takes billions of years to arrive, and every measurement carries uncertainty. The pursuit is therefore an act of patience, of refining methods, of checking and rechecking, of accepting that knowledge comes slowly. As new instruments come online, gravitational wave detectors, space telescopes, ground-based surveys, the pursuit continues. Gravitational waves from merging neutron stars offer a new way to measure distances, independent of the traditional ladder. These events, sometimes called standard sirens, provide fresh data that may help resolve the tension. The pursuit of the Hubble constant is a reminder that science is never finished. Each answer leads to new questions, each measurement to new puzzles. The expansion rate is now known to within a few percent, but that last bit of precision, that final reconciliation of different methods, remains elusive. It is a chase that may take decades more, but the effort is worth it, because in that number lies the story of the cosmos. As you let this thought drift, imagine astronomers scattered across the world, each with their telescopes pointed upward, each measuring distances, recording redshifts, refining the cosmic map. They are not racing against one another, but toward understanding. The pursuit is slow, steady, and patient. Much like the expansion of the universe itself, the universe does not give up its secrets easily. Every piece of evidence, every clue about its nature, must be extracted with care from the faint signals that reach us across cosmic distances. The expansion of space is no exception. To understand it, astronomers have gathered fragments of data, light from distant galaxies, subtle shifts in wavelength, patterns in the distribution of matter, and woven them into a coherent picture. The most direct clue is the redshift. When light from a distant galaxy is spread into a spectrum, the familiar patterns of hydrogen, helium, and other elements appear, but shifted toward longer wavelengths. This shift is proportional to the galaxy's distance. The farther away it is, the more its light is stretched. By measuring redshifts across hundreds of thousands of galaxies, astronomers have confirmed that the expansion is real and follows a predictable pattern. To understand expansion, we must also know how far away these galaxies are, and distance is notoriously difficult to measure in astronomy. The cosmic distance ladder, built rung by rung, provides the framework. Parallax measurements anchor the nearby stars. Cepheid variables extend the ladder to nearby galaxies. Type Ia supernovae reach even farther, across billions of light years. Each method has its own uncertainties, its own potential for error. Cepheids can be obscured by dust, making them appear dimmer than they are. Supernovae are not perfectly uniform. There are subtle variations that must be accounted for. The challenge is to cross-check, to use multiple methods, to ensure that the measurements are consistent. One of the most important clues came not from individual galaxies, but from the faint glow that fills the entire sky. In 1965, Arno Penzias and Robert Wilson detected a uniform microwave radiation coming from all directions. At first, they thought it was noise, interference from their equipment or from nearby sources. But no matter what they did, the signal persisted. What they had found was the cosmic microwave background, the afterglow of the Big Bang. This radiation was released when the universe was only about 380,000 years old, when it cooled enough for atoms to form and light to travel freely. Over the billions of years since, that light has been stretched by the expansion of space, shifting from visible wavelengths into microwaves. The cosmic microwave background is a snapshot of the early universe, a fossil record of conditions long before galaxies formed. Tiny fluctuations in its temperature, measured with satellites like WMAP and Planck, reveal information about the density and composition of the cosmos at that early time. By modeling how those conditions evolved, cosmologists can predict the expansion rate today. This method, based on the microwave background, gives a different perspective from the distance ladder. It looks back to the early universe and projects forward, using the laws of physics to infer how the cosmos should have evolved. The fact that this method gives a slightly different value for the Hubble constant is one of the central puzzles of modern cosmology. Another clue comes from the large-scale structure of the universe. Galaxies are not scattered randomly. They cluster together into groups, which form filaments and walls surrounding vast voids. This cosmic web is shaped by gravity, by the pull of dark matter, and by the expansion of space. By mapping this structure, astronomers can test models of how the universe evolved and refine their understanding of expansion. Gravitational lensing offers yet another clue. When light from a distant galaxy passes by a massive foreground object, like a cluster of galaxies, its path is bent by gravity. This bending can distort the image, creating arcs or multiple images of the same galaxy. By studying these distortions, astronomers can measure the mass of the foreground object and the distances involved. Gravitational lensing provides an independent check on the cosmic distance ladder. More recently, gravitational waves have entered the picture. When two neutron stars or black holes merge, they produce ripples in spacetime that travel outward at the speed of light. These waves can be detected by instruments like LIGO and Virgo. If the merger also produces light, a kilonova or other electromagnetic signal, then both the gravitational wave and the light can be observed. This allows astronomers to measure the distance to the event directly, providing a new kind of standard candle, or rather, a standard siren. Each of these clues, redshifts, Cepheids, supernovae, the microwave background, large-scale structure, gravitational lensing, gravitational waves, adds a piece to the puzzle. No single method is perfect. Each has its strengths and weaknesses, its uncertainties and assumptions, but together they form a web of evidence that supports the picture of an expanding universe. What makes these clues so compelling is that they come from different sources, different methods, different wavelengths of light. They are independent checks on the same underlying reality. When multiple methods converge on the same conclusion, confidence grows. The expansion is not a theoretical speculation, it is an observed fact, confirmed by fragments of data gathered from across the cosmos. The process of gathering these clues is painstaking. It requires decades of observations, careful calibration of instruments, rigorous analysis of data. It is not glamorous work. It is patient, methodical, often frustrating, but it is also deeply satisfying, because each new clue brings us closer to understanding the universe we inhabit. As you rest now, imagine those clues scattered across the night sky. Each galaxy a data point, each redshift a message, each photon a messenger from the past. The universe speaks to us in whispers, in faint signals stretched across billions of years, and we listen, piece by piece, fragment by fragment, assembling the story of expansion. By the late 20th century, cosmologists had grown comfortable with the idea of an expanding universe. The data were clear, the models well tested, the story seemed settled. The universe began in a hot, dense state, the Big Bang, and had been expanding ever since. Gravity, pulling on all the matter in the cosmos, was thought to be slowing that expansion, like a ball thrown upward that gradually loses speed. The question was not whether the expansion would slow, but whether it would slow enough to halt entirely, leading to a collapse, or whether it would coast forever. Then, in the late 1990s, two independent teams of astronomers set out to measure the rate of deceleration by observing distant Type Ia supernovae. These stellar explosions are so bright that they can be seen across billions of light years, and their uniform brightness makes them ideal for measuring cosmic distances. By comparing their apparent brightness with their redshifts, astronomers could calculate how fast the universe was expanding at different times in its history. The teams expected to find that the expansion was slowing, but when they analyzed the data, they found the opposite. The distant supernovae were fainter than expected, which meant they were farther away than they should be. The universe was not decelerating, it was accelerating. This result was so unexpected that the teams checked and rechecked their data, looking for errors. Could dust be obscuring the supernovae, making them appear dimmer? Could there be something wrong with the distance ladder? But no matter how they tested the data, the conclusion remained. The expansion of the universe was speeding up. The discovery earned the Nobel Prize in Physics in 2011, but more importantly, it introduced one of the greatest mysteries in modern cosmology. What could be driving the acceleration? Gravity pulls matter together. It should be slowing the expansion, not speeding it up. Something else, something invisible and pervasive, must be pushing the cosmos apart. This unknown force came to be called dark energy. The name is a placeholder, a label for something we do not yet understand. It appears to be a property of space itself, a kind of energy that exerts a repulsive effect, counteracting gravity on the largest scales. Unlike dark matter, which clumps together and forms structures, dark energy is smooth, uniform, woven into the very fabric of the cosmos. Current estimates suggest that nearly 70% of the energy content of the universe is in this form. Everything we see, stars, planets, gas, dust, makes up less than 5%. Dark matter accounts for about a quarter, and dark energy dominates the rest. The universe, in other words, is mostly made of something we do not comprehend. One way to think about dark energy is as a cosmological constant, the term Einstein once added to his equations to force a static universe. If empty space has a constant energy density, then as the universe expands and more space appears, the total energy increases, driving faster expansion. This interpretation matches the observations reasonably well, but it raises profound questions. Why should empty space have energy? Why this amount and not another? Another possibility is that dark energy is not constant but dynamic, perhaps related to a new field that changes over time. Some theorists call this quintessence, a hypothetical energy field that evolves as the universe expands. If dark energy is quintessence, its influence may grow or diminish in the future, altering the ultimate fate of the cosmos. But so far, observations have not shown any deviation from the simplest model of a constant vacuum energy. The mystery of dark energy is sharpened by a striking problem known as the cosmological constant problem. When physicists calculate the energy of the vacuum using quantum field theory, the result is vastly larger, by a factor of up to 10 to the 120th power, than what is observed in cosmology. This is sometimes called the worst theoretical prediction in physics. Why the observed value is so small, yet not zero, is an open puzzle. The discovery of dark energy changed how we think about the future of the universe. If the expansion is accelerating, then galaxies will continue to recede faster and faster. Already, galaxies beyond a certain distance are moving away faster than light, not because they are traveling through space at superluminal speeds, but because space itself is stretching between us. Their light will never reach us. no matter how long we wait. As acceleration continues, more galaxies will cross this horizon, vanishing from view. Future observers in our galaxy may see only a handful of nearby systems, unaware of the vast cosmos we know today. In some models, dark energy could even lead to a dramatic end known as the Big Rip. If the acceleration grows without limit, it could eventually overcome not just the gravity-binding galaxies, but the forces holding stars, planets, and even atoms together. In this scenario, the universe would tear itself apart. Whether this fate awaits us depends on the nature of dark energy. If it is a true cosmological constant, the expansion will accelerate forever, but never reach the catastrophic rip. If it is more exotic, the future could be stranger still. The deeper mystery is not just what dark energy is, but why we discovered it now. For most of cosmic history, matter and radiation dominated. Only in the last few billion years has dark energy begun to take over, driving the acceleration we observe. This timing seems coincidental. Why should we live in the era when dark energy becomes important? Or is it not a coincidence at all, but a requirement? Perhaps only in such an era could observers like us exist, able to see both the expansion and the acceleration. As you let this thought rest, imagine the universe as a vast ocean. On its surface, waves rise and fall, galaxies cluster and recede. But beneath the surface, something invisible stirs, a current that pulls everything apart. That current is dark energy, and it rules the cosmos. In science, there are moments when everything changes. Not gradually, not through the slow accumulation of evidence, but suddenly, in a revelation that overturns assumptions and reshapes understanding. The discovery that the expansion of the universe is accelerating was one of those moments. It was a paradigm shift, a transformation of how we see the cosmos and our place within it. Before 1998, cosmologists had a clear picture of the universe's fate. The cosmos was expanding, yes, but gravity was slowing it down. The question was whether there was enough matter to halt the expansion entirely, leading to a collapse, or whether the expansion would continue forever. Gradually thinning out into darkness, the universe was thought to be coasting, like a car rolling to a stop after the engine is cut. The discovery of acceleration shattered that picture. The universe was not coasting, it was accelerating, as if an invisible hand had pressed the gas pedal. This was not just a refinement of the old model, it was a complete reversal, a sign that something fundamental had been missed. The paradigm shift was not immediate. When the first results were announced, many in the scientific community were skeptical. The data came from distant supernovae, and supernovae are complex events. Could there be systematic errors? Could dust or other factors be skewing the results? The teams themselves were cautious, checking and rechecking before going public. But as more data came in, from independent observations and different methods, the evidence became undeniable. The universe was accelerating, and that meant something new, something unknown, was at work. Dark energy, as it came to be called, was not just a minor correction to cosmology, it was the dominant component of the universe, making up 70% of its energy content. The shift in thinking was profound. For decades, cosmologists had focused on matter, on how galaxies formed, how stars ignited, how structures grew under the pull of gravity. Dark matter, though mysterious, could at least be understood as a gravitational player, something that clumped and clustered. But dark energy was different. It did not clump. It did not form structures. It was smooth, uniform, and repulsive. It dominated the cosmos, yet it left no direct trace. The paradigm shift also changed how we think about the universe's history. In the early cosmos, matter and radiation dominated, and gravity pulled things together. Galaxies formed, stars ignited, and the universe evolved through a series of recognizable stages. But as the universe expanded, the density of matter decreased, while dark energy remained constant. This transition marks a turning point in cosmic history. Before it, the universe was shaped by gravity, by the clumping of matter into structures. After it, the universe is shaped by dark energy, by the smooth repulsion that drives galaxies apart. We live near that transition, in an era when both forces are significant, when we can still see the structures formed by gravity, but also witness the acceleration driven by dark energy. The paradigm shift also raised new questions. If dark energy dominates the universe, what is it? Is it a property of space itself, as the cosmological constant suggests? Or is it a new field, something dynamic that evolves over time? And why is its energy density so finely tuned? If it were much larger, galaxies would never have formed. If it were much smaller, it would have no effect. The fact that it is just right to allow structures to form, yet strong enough to dominate eventually, seems almost too convenient. This puzzle has led some to invoke the anthropic principle, the idea that we observe these properties because they are necessary for our existence. In a universe with much larger dark energy, no observers would exist to measure it. In a universe with no dark energy, the cosmos would look different, but observers might still arise. The fact that we find ourselves in a universe with just this amount of dark energy may be a selection effect, a consequence of living in one of many possible universes. The paradigm shift extended beyond cosmology. It touched physics, philosophy, even theology. If the universe is accelerating, what does that mean for its ultimate fate? If dark energy continues to dominate, the cosmos will grow colder, emptier, darker. This vision is bleak, but it is also a reminder of impermanence, of the fleeting nature of structure and light. Yet the shift also brought a sense of wonder. The universe is stranger than we imagined. It is not a static backdrop, not a simple machine winding down. It is dynamic, surprising, full of mysteries we have not yet solved. The discovery of dark energy did not close the book on cosmology. It opened new chapters, new questions, new frontiers to explore. The paradigm shift teaches us that science is always provisional. What we know today may be overturned tomorrow by a single observation, a single experiment, a single calculation. The cosmos does not yield its secrets easily, and every answer leads to deeper questions. To live through a paradigm shift is to witness science in action, to see how our understanding evolves, how we adapt when reality defies expectation. As you let this settle, imagine the moment when the data first revealed the acceleration. Picture the astronomers staring at their results, disbelief giving way to realization. The universe was not what they thought. It was something stranger, something new. That moment changed everything. When the discovery of cosmic acceleration was announced, the immediate ripple spread quickly through the scientific community. Astronomers, physicists, and cosmologists gathered at conferences, wrote papers, debated the implications. The news appeared in journals, in popular science magazines, in newspapers. For a brief moment, the expansion of the universe was front-page news, and people who had never thought about cosmology found themselves pondering the fate of everything. The first ripple was one of adjustment. Textbooks had to be rewritten. Models of the universe's history had to be revised. The old diagrams, showing a cosmos coasting or collapsing, were replaced with new ones, showing an accelerating expansion driven by dark energy. Students learning cosmology for the first time now encountered a universe radically different from the one their teachers had studied. Funding agencies took notice. If the universe was dominated by something unknown, then understanding that something became a priority. New observatories were proposed, new satellites designed, new experiments funded. The search for dark energy became one of the central missions of 21st century astronomy. Alongside the search for dark matter and the quest to understand the Big Bang, the ripple also reached adjacent fields. Particle physicists, who study the smallest scales of reality, began to wonder if dark energy was connected to the vacuum energy predicted by quantum field theory. If so, why was the observed value so much smaller than the theoretical prediction? This mismatch, known as the cosmological constant problem, became a bridge between cosmology and quantum mechanics, two fields that had long operated independently. Philosophers joined the conversation as well. If the universe was accelerating toward emptiness, what did that mean for meaning itself? Was the cosmos indifferent to life, to consciousness, to the questions we ask? The discovery of dark energy did not answer these questions, but it sharpened them, giving them a concrete context. The universe has a fate, and that fate is cold and empty. How do we live with that knowledge? Theologians also engaged with the discovery, though their responses varied. Some saw the acceleration as evidence of a cosmos beyond human control, a reminder of limits and finitude. Others saw it as a continuation of creation, a universe still unfolding according to laws we are only beginning to understand. The conversation between science and faith, always complex, gained a new dimension. But beyond the academic and philosophical ripples, there was a more personal effect. People who heard about the discovery, who read about dark energy and the accelerating expansion, found themselves looking at the night sky differently. The stars were no longer just distant lights. They were part of a cosmos in motion, a universe racing toward an uncertain future. The knowledge did not diminish the beauty of the sky. If anything, it deepened it, adding a layer of poignancy to every glimmer. The immediate ripple also included challenges. The discovery raised as many questions as it answered. What is dark energy? Is it constant or changing? Can it be detected directly or only through its gravitational effects? These questions demanded new observations, new experiments, new ways of probing the cosmos. The ripple was not a wave that passed and left things unchanged. It was the beginning of a new era of inquiry. Within cosmology, the ripple forced a reassessment of priorities. For decades, the focus had been on understanding the formation of galaxies, the role of dark matter, the details of the cosmic microwave background. Now, dark energy took center stage. It was the largest component of the universe, yet the least understood. Researchers shifted their attention, designing surveys to map the distribution of galaxies, using supernovae and other distance indicators to trace the expansion history, searching for any deviation from a cosmological constant. The discovery also prompted a re-evaluation of the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. If dark energy is smooth and uniform, then the principle holds. But if dark energy varies from place to place, or if it evolves over time, then the universe might be more complex than the simple models suggest. The ripple extended into these foundational assumptions, questioning what we thought we knew. There was also an emotional ripple, harder to quantify, but no less real. The discovery of acceleration is, in a sense, a discovery of ending. It tells us that the universe will not collapse and be reborn. It will not reach a steady state and remain there forever. It will expand and accelerate until the galaxies are scattered beyond reach, until the stars burn out, until the cosmos is cold and dark. This is not a comforting vision, but it is an honest one, and there is a strange solace in facing reality without illusion. For some, the immediate ripple was a call to action. If the universe has a finite span during which structures can form, during which life can exist, then our time is precious. The knowledge of cosmic fate does not make life meaningless. It makes it urgent, beautiful. The ripple reminded us that we are part of a larger story, one that began billions of years ago and will continue for trillions more, but one in which our chapter is brief. As you rest now, imagine those ripples spreading outward from the discovery, touching scientists, philosophers, students, anyone who paused to wonder, is accelerating. That simple fact changed how we see everything. And the ripples continue still, spreading through time, shaping how we explore, how we question, how we live. The discovery that the universe is accelerating will echo through time long after the scientists who made it are gone. It is one of those revelations that reshapes not just a field of study, but our understanding of existence itself. The echoes are not confined to the present. They reach backward, illuminating the past, and forward, shaping how future generations will see the cosmos. Looking backward, the discovery casts new light on the history of cosmology. When Edwin Hubble first measured the expansion in the 1920s, he could not have known that the expansion was accelerating. The tools were not precise enough, the distances not great enough, but his work laid the foundation for everything that followed. The echoes of his observations resonate through the decades, connecting his measurements to the supernova surveys of the 1990s and onward to the observatories of today. Einstein's cosmological constant, once dismissed as a blunder, has been resurrected by the discovery of dark energy. The term he added to his equations to force a static universe may, in fact, describe a real property of space. The echoes reach back to Einstein's equations, written over a century ago, and show that they contained a hint of dark energy all along, waiting to be recognized. The discovery also echoes through the history of ideas. Philosophers have long asked whether the universe is eternal or finite, whether it has a purpose or is indifferent. The acceleration does not answer these questions definitively, but it shifts the ground on which they are asked. The cosmos has a history and a future, and both are shaped by forces we are only beginning to understand. The echoes of these ideas will influence philosophy for generations to come. Looking forward, the echoes shape what future astronomers will see. As the acceleration continues, galaxies beyond our local group will recede faster and faster. In 1 trillion years, or perhaps sooner, they will vanish beyond the cosmic horizon. Future observers will see a much emptier sky, devoid of the billions of galaxies we can observe today. The echoes of our discovery will be their starting point, a historical record of a time when the universe was fuller, richer, more observable. Those future astronomers may struggle to reconstruct the history we know. Without distant galaxies to measure, without the cosmic microwave background visible in their skies, they may lack the evidence needed to infer the Big Bang or the acceleration. The echoes of our knowledge, preserved in records and archives, may be their only link to a past they cannot observe directly. The discovery also echoes into the future of physics. The mystery of dark energy remains unsolved. Future scientists, with better instruments and deeper theories, may finally understand what it is. Perhaps they will discover that it is not a cosmological constant, but a dynamic field. Perhaps they will find a connection to quantum gravity, a unification that explains both the smallest and largest scales. The echoes of today's discovery will guide that search, shaping the questions asked and the experiments designed. The echoes also touch the future of humanity. If we survive as a species for millions or billions of years, we may witness cosmic changes that are invisible on human timescales. We may see the Milky Way merge with Andromeda, forming a new galaxy. We may see distant galaxies disappear beyond the horizon, one by one. The knowledge of acceleration, of dark energy, will shape how we understand and navigate that future. There is also an echo in the way we think about meaning. The universe is not designed for us. It is not fine-tuned to ensure our comfort or survival. It is a vast, dynamic system governed by laws that care nothing for intentions or purposes. Yet we are here, asking questions, seeking understanding. The echoes of the discovery remind us that meaning is something we create, not something the cosmos provides. We find significance in the act of discovery itself, in the pursuit of knowledge, in the wonder of looking up at the stars. The echoes through time are not just intellectual, they are emotional, existential. To know that the universe is accelerating is to know that everything is temporary. The galaxies will scatter, the stars will fade, the cosmos will grow cold. This is not a message of despair, but of perspective. Our lives are brief, but they are part of a story that began with the Big Bang and will continue for trillions of years. The echoes connect us to that story, making us participants in something larger than ourselves. In literature, art, and music, the echoes will also sound. The image of an accelerating universe, of galaxies fleeing into darkness, is a powerful metaphor. It speaks to themes of loss of change, of the passage of time. Artists will draw on the discovery, creating works that explore its emotional and philosophical dimensions. The echoes will shape culture as well as science. The echoes also serve as a reminder of the power of curiosity. The discovery of acceleration was not driven by practical concerns or immediate needs. It was driven by the desire to understand, to measure, to know. That impulse, the curiosity that sends us reaching for the stars, is one of the defining traits of our species. The echoes of this discovery will inspire future generations to keep asking questions, to keep looking deeper, to keep seeking the unknown. As you let this thought rest, imagine those echoes spreading outward and forward, touching minds and hearts across centuries. The universe is accelerating, and that knowledge will never be forgotten. It will echo through time, shaping how we see ourselves, how we see the cosmos, and how we live in the brief moment we are given. Behind every great discovery, there are people. Not abstract figures in textbooks, but human beings with hopes, doubts, late nights, and moments of insight. The story of the expanding universe is not just about equations and telescopes. It is about dreamers who dared to ask impossible questions and who devoted their lives to answering them. Edwin Hubble was one such dreamer. Born in 1889 in Missouri, he was not destined from birth to become an astronomer. He studied law, taught high school, even considered a career in boxing. But the pull of the stars was too strong. He returned to school, earned his doctorate in astronomy, and eventually found himself at Mount Wilson Observatory, peering through the largest telescope in the world. Hubble's genius was not in wild speculation but in patient observation. He measured, catalogued, compared. He identified Cepheid variables in distant nebulae, calculated their distances, and revealed that the universe was far larger than anyone had imagined. He measured redshifts, plotted velocities against distances, and discovered the expansion. His work was meticulous, careful, built on thousands of hours at the telescope. He was a dreamer, yes, but also a craftsman. Georges Lemaitre was another dreamer, though his path was different. Born in Belgium in 1894, Lemaitre was both a physicist and a Catholic priest. For him, science and faith were not enemies, but partners in the search for truth. He studied Einstein's equations and saw in them the possibility of an expanding universe. In 1927, before Hubble's observations were widely known, Lemaitre proposed that the cosmos had begun from what he called a primeval atom, a single point that exploded outward in a cosmic firework. Lemaitre's vision was bold, almost poetic. He imagined the universe as a story with a beginning, a middle, and perhaps an end. His work was initially overlooked, published in a Belgian journal that few outside Europe read. But eventually, his ideas reached a wider audience, and the primeval atom hypothesis became the foundation of what we now call the Big Bang theory. Lemaitre was a dreamer who saw creation in mathematics, who found wonder in the expansion of space. Milton Humason was a dreamer of a different sort. He began his career not as an astronomer, but as a mule driver, hauling supplies up the steep slopes of Mount Wilson to the observatory under construction. He had no formal education beyond high school, no degrees or credentials, but he had curiosity and he had skill. He learned to operate the telescopes, to take photographic plates, to measure spectra. Eventually, he became one of the most skilled observers of his generation, working alongside Hubble to gather the data that revealed the expanding universe. Humason's story is a reminder that dreamers come from all backgrounds. You do not need a pedigree to contribute to science. You need patience, dedication, and a willingness to look carefully at the world. Humason looked, and what he saw changed everything. Vera Rubin was another dreamer, born in 1928 in Philadelphia. As a young woman, she fell in love with the stars, spending nights watching them from her bedroom window. She pursued astronomy, despite discouragement, despite being told that women did not belong in the field. She studied the rotation of galaxies and discovered that stars on the outskirts moved faster than they should, given the visible matter. Her work provided some of the strongest evidence for dark matter, the invisible substance that makes up most of the universe's mass. Rubin's contribution to cosmology was profound, though it took years for her work to receive the recognition it deserved. She was a dreamer who refused to be discouraged, who kept asking questions even when others doubted her. Her legacy is not just in the data she gathered, but in the doors she opened for those who came after. The dreamers of cosmology are not just individuals, they are teams, communities, generations of scientists building on one another's work. The discovery of the cosmic microwave background, for instance, was made by Arno Penzias and Robert Wilson, two radio astronomers who stumbled upon it while trying to eliminate noise from their equipment. But their discovery was only possible because of earlier theoretical work by George Gamow, Ralph Alpher, and Robert Herman, who predicted that the Big Bang should have left behind a faint glow of radiation. The dreamers include those who built the instruments, the engineers who designed telescopes and satellites, the technicians who maintained them, the programmers who wrote the software to analyze the data. They include the theorists who developed the mathematics of general relativity, the statisticians who refined the methods for measuring distances, the educators who taught the next generation. Every discovery is a collective effort, built on countless small contributions. What unites these dreamers is not genius or fame, though some achieved both. It is curiosity. It is the willingness to look up at the night sky and ask, what is that? How far away is it? How fast is it moving? Why? These are simple questions, but they lead to profound answers. The dreamers are those who cannot stop asking, who cannot accept ignorance as final, who keep pushing at the boundaries of what is known. The story of the expanding universe is, in the end, a human story. It is about people who devoted their lives to understanding the cosmos, who sacrificed comfort and certainty for the chance to glimpse something larger. They were not superhuman. They made mistakes, had doubts, faced failures, but they kept going, driven by a love of knowledge, a hunger for truth. As you let this thought settle, imagine those dreamers scattered across time. Hubble at his telescope, Lemaitre at his desk, Humason on the mountain, Rubin peering at galaxy rotation curves. Each one a person, each one asking questions. Together, they built our understanding of the universe. And their work continues in the dreamers of today, still asking, still exploring, still reaching for the stars. The pursuit of truth in science is not always smooth. It is often marked by skepticism, debate, and resistance. When new ideas challenge old assumptions, they are met not with open arms, but with scrutiny. This is as it should be. Science advances not by accepting every claim, but by testing, questioning, and demanding evidence. The story of the expanding universe is also a story of the battle for truth, of ideas that were challenged, defended, and ultimately accepted. When Edwin Hubble first presented his evidence for the expansion, not everyone was convinced. Some astronomers questioned his distance measurements. Were the Cepheid variables he used truly reliable? Could there be systematic errors that skewed the results? Others questioned the interpretation of redshifts. Could they be caused by something other than motion, by tired light or gravitational effects? The battle was not personal. It was scientific, a necessary part of the process. Hubble responded with more data. He measured more galaxies, refined his methods, collaborated with others. The evidence accumulated, and gradually the skepticism faded. But the battle did not end there. Even as the expansion became accepted, new battles emerged over what it meant. The debate between the Big Bang and the steady-state theory was one such battle. Fred Hoyle and his colleagues defended the steady-state model, which proposed that the universe was eternal, with no beginning. They saw the Big Bang as philosophically troubling, too close to religious creation myths. The battle was fought in journals, at conferences, in radio broadcasts. Hoyle was eloquent, persuasive, and wrong. But his resistance was not obstinate, it was principled. He demanded evidence, and when the evidence came in the form of the cosmic, microwave background, he eventually conceded. The discovery of the cosmic microwave background in 1965 was a turning point in the battle. Arno Penzias and Robert Wilson detected a faint uniform glow of radiation coming from all directions. This was precisely what the Big Bang theory predicted, the cooled remnant of the early universe's heat. The steady-state theory had no explanation for it. The battle was not over immediately, but the tide had turned. Within a few years, the Big Bang became the dominant framework, and the steady-state theory faded into history. But new battles arose. In the 1980s and 90s, cosmologists debated the value of the Hubble constant. Different teams, using different methods, arrived at different numbers. Some measurements suggested a fast expansion, implying a young universe, only 10 billion years old. Others suggested a slower expansion, implying greater age. The discrepancy was troubling. It suggested that something was wrong, either with the measurements or with the underlying assumptions. The battle over the Hubble constant was resolved gradually through improved observations and refined techniques. The launch of the Hubble Space Telescope allowed astronomers to measure Cepheids in distant galaxies with unprecedented precision. The value of the Hubble constant converged, and the age of the universe settled near 14 billion years. But even today, a new tension has emerged, with different methods yielding slightly different results. The battle continues. The discovery of cosmic acceleration in 1998 sparked another battle. When the supernova teams announced that the expansion was speeding up, many in the community were skeptical. The result was so unexpected, so contrary to intuition, that it demanded extraordinary evidence. The teams provided it with multiple independent observations, careful checks for systematic errors, and confirmations from other methods. The skepticism was healthy, but eventually the evidence won. The battle for truth is not just about big questions. It is also about details, about calibrations, about assumptions. Every measurement in cosmology rests on a chain of reasoning, and every link in that chain must be tested. When one team finds a result that another cannot reproduce, there is a battle to understand why. Is it a real effect or an artifact? The resolution comes through collaboration, through sharing data, through independent verification. What makes these battles productive is that they are governed by rules. In science, authority does not determine truth. Evidence does. It does not matter how famous you are, how many papers you have written, or how elegant your theory is. If the data contradict you, you are wrong. This can be painful, especially for those who have invested years in a particular idea. But it is also liberating. It means that truth is accessible to anyone willing to follow the evidence. The battle for truth also involves admitting uncertainty. Science is not about absolute certainty. It is about probabilities, about confidence levels, about acknowledging what we do not know. When cosmologists say the universe is 14 billion years old, they mean it with a margin of error. When they say dark energy makes up 70% of the cosmos, they mean it based on current models and observations, which may be revised. The battle is not to reach final, unchanging truth, but to approach it asymptotically, getting closer with each generation. There is something deeply human about these battles. They involve ego, ambition, pride, but they also involve humility, collaboration, and a shared commitment to understanding. Scientists argue fiercely, but they also listen, adapt, and change their minds when the evidence demands it. The battle for truth is not a war. It is a conversation, sometimes heated, sometimes contentious, but always moving toward greater clarity. The expanding universe was not accepted because a single genius declared it so. It was accepted because many people, over many years, tested the idea, challenged it, refined it, and found it to hold up. The battle for truth is ongoing. New observations, new theories, new questions will spark new debates. And that is good, because the battle is how science stays honest, how it avoids dogma, how it continues to grow. As you rest now, imagine those battles, not as conflicts but as conversations. Picture scientists in lecture halls pointing at graphs, debating interpretations. Picture them at telescopes, gathering data, checking and rechecking. The battle for truth is the heartbeat of science, the rhythm by which it moves forward. To live in the 21st century is to possess a kind of awareness that no previous generation had. We know, with precision and confidence, that the universe is expanding. We know that it began nearly 14 billion years ago in a hot, dense state. We know that it is accelerating, driven by dark energy. We know that we live on a small planet orbiting an ordinary star in one galaxy among billions, all rushing away from one another across a cosmos that stretches far beyond what we can see. This awareness changes how we see ourselves. For most of human history, people believed they lived at the center of creation. The earth was the stage, the heavens a backdrop, the stars were fixed lights, eternal and unchanging. The universe was thought to be small, comprehensible, designed with humanity in mind. That worldview offered comfort, certainty, a sense of purpose. The expanding universe has taken that comfort away, or at least transformed it. We are not at the center. We are not the point of it all. The cosmos does not revolve around us. It barely notices us. The awareness of this can feel diminishing, as if we have been reduced to insignificance. And in one sense, we have. On the scale of the universe, we are tiny, brief, almost invisible. But there is another way to see it. The awareness of our smallness is also an awareness of our connection. We are made of the same atoms as the stars. The carbon in our bodies was forged in the cores of ancient suns. The oxygen we breathe, the iron in our blood, all of it came from stellar nucleosynthesis, from the deaths of stars that exploded long before the Earth existed. We are not separate from the universe. We are part of it, woven into its fabric, participants in its unfolding. The new awareness also includes the recognition of limits. There are horizons beyond which we cannot see, not because our instruments are too weak, but because the expansion of space prevents light from reaching us. There are questions we may never answer, mysteries that lie forever beyond our grasp. This could be frustrating, but it can also be freeing. It means we do not have to know everything to appreciate what we do know. To be aware of the expanding universe is to be aware of time in a new way. Time is not just the ticking of a clock or the turning of seasons. It is the unfolding of cosmic history, the stretching of space, the cooling of the cosmos, from a hot beginning toward a cold end. Our lives are brief flickers in that vast span, moments of consciousness in a universe that existed long before us and will continue long after. This awareness can shift how we think about meaning. If the universe is not designed for us, if it has no inherent purpose, then meaning is not something we discover. It is something we create. We find significance in our relationships, our work, our curiosity, our love. The expanding universe does not give us meaning, but it gives us context, a stage on which to live our lives, knowing they are temporary, but also knowing they are real. The awareness also brings a kind of humility. To know that the universe is so vast, so old, so full of mysteries we have not yet solved, is to recognize the limits of human knowledge. We have learned an astonishing amount in the last century, but we have also learned how much we do not know. Dark matter, dark energy, the quantum nature of space-time, the possibility of other universes. All of these are reminders that the cosmos still holds secrets, yet the awareness is not paralyzing, it is energizing. Knowing that there are mysteries to solve, horizons to explore, questions to ask, gives us direction. It gives us something to reach for. The expanding universe invites us to keep looking, keep wondering, keep pushing at the boundaries of what is known. The awareness is not an endpoint. It is a beginning. There is also a collective dimension to this awareness. We share it. Every person who looks up at the night sky, every student who learns about the Big Bang, every scientist who measures a redshift, participates in the same understanding. We are all passengers on the same small planet, all witnesses to the same unfolding cosmos. The awareness connects us, not just to the universe, but to one another. The new awareness also shapes how we think about the future. If the universe is accelerating, if galaxies are disappearing beyond the horizon, then the era we live in is special. Future observers may not have access to the evidence we have. They may not see distant galaxies, may not detect the cosmic microwave background, may not know that the universe began in a Big Bang. We are privileged to live in a time when the cosmos is still legible, when its history is still written in the light we can observe. To be aware of this is to feel a sense of responsibility. The knowledge we gather today may be the only record of certain cosmic truths. Future generations may depend on our observations, our measurements, our archives. The awareness is not just intellectual, it is also custodial. We are stewards of cosmic knowledge, passing it forward to those who will come after. As you rest now, picture that awareness spreading across humanity. Imagine people in different places, different times, all looking up at the same stars, all wondering about the same questions. The expanding universe is not just a fact, it is a shared realization, a collective awakening to the nature of reality, and it changes us. After all the observations, all the measurements, all the theories, there is a question that remains. What does the expansion of the universe reveal about the nature of reality itself? What is the deepest truth hidden in the red shifts, the acceleration, the horizons? This is not a question that can be answered with equations alone. It requires stepping back, looking at the whole picture, and asking what it all means. The deepest truth may be this: the universe is not static. It is not a fixed stage on which events unfold. It is dynamic, changing, alive in a way we do not usually think of as alive. Space itself is not an empty container, but an active participant in the cosmic drama. It stretches, curves, responds to matter and energy. The expansion is not something happening in the universe. It is something the universe is doing. This overturns centuries of intuition. Since the time of Newton, space and time were thought of as absolute, unchanging frameworks. Objects moved through space, time ticked forward, but the frameworks themselves were fixed. Einstein's theory of general relativity changed that. It revealed that space and time are woven together into space-time, a fabric that can bend and stretch. The expansion of the universe is the most dramatic example of this. The fabric itself is growing. To grasp this is to see reality differently. We think of objects as things that exist in space. But if space is expanding, then in some sense, space is also a thing, something with properties, something that changes. The deepest truth is that the universe is not a collection of objects in a container. It is a process, an unfolding, a becoming. This truth connects to the question of time. If the universe is expanding, then it has a history. It was once smaller, denser, hotter. If you run the expansion backward, you reach a point where the universe was infinitely dense, a singularity, the Big Bang. Time itself began at that moment. There is no before, because before requires time, and time did not exist. The deepest truth is that time is not eternal. It has a beginning, and it may have an end. This challenges our everyday sense of time as something that flows forever, unchanging, independent of events. But in cosmology, time is tied to the expansion. The age of the universe is measured by how long space has been stretching. Time and space are not separate. They are aspects of the same thing, space-time, and they are both finite in the past, beginning with the Big Bang. The deepest truth also includes the realization that the universe is mostly unknown. We can see galaxies, stars, planets, but they make up less than 5% of the cosmos. The rest is dark matter and dark energy. Substances we cannot see, cannot touch, can only infer from their gravitational effects. The universe we observe directly is a tiny fraction of what exists. The deepest truth is that reality is larger, stranger, More hidden than our senses reveal, this unknown majority shapes the fate of the cosmos. Dark matter holds galaxies together, forms the scaffolding on which structures grow. Dark energy drives the acceleration, pushing galaxies apart, determining whether the universe will expand forever or undergo some other transformation. The deepest truth is that the universe is not governed by the things we can see, but by the things we cannot. There is also a truth about perspective. The expansion appears the same from every vantage point. There is no center, no privileged location. Every observer, no matter where they are, sees the same pattern of recession. This principle, the cosmological principle, suggests that the universe is fundamentally democratic. No place is special. No observer is favored. The deepest truth is that we are not at the center, but neither is anyone else. The cosmos is impartial. This impartiality can feel cold, but it is also liberating. It means that the laws of physics are the same everywhere, that the universe is comprehensible, that what we learn here applies out there. The deepest truth is that the cosmos is unified, governed by consistent laws, even if those laws produce complexity and diversity. Another layer of the deepest truth is about impermanence. The universe is not eternal in its current form. It had a beginning, and it will have an ending, or at least a transformation. The stars will fade, the galaxies will scatter, the cosmos will cool. Nothing lasts forever. Structures are temporary, fleeting arrangements of matter and energy that arise, persist for a time, and dissolve. The deepest truth is that everything changes, and change is not a flaw. It is the nature of reality. This can be difficult to accept. We crave permanence, stability, things we can rely on. But the expanding universe teaches us that permanence is an illusion. The only constant is change. And yet, within that change, there is beauty. The fact that stars burn out does not make them less beautiful. The fact that galaxies scatter does not make them less wondrous. The deepest truth is that impermanence and beauty are not opposites. They are companions. There is also a truth about knowledge itself. The expanding universe reveals that the cosmos is knowable, at least in part. We can measure distances, calculate rates, predict futures. We can look at light from billions of years ago and infer what the universe was like. This is astonishing. It means that reality is not arbitrary, not random, but structured. It follows laws we can discover. The deepest truth is that the universe makes sense, even if it does not care whether we understand it. Finally, the deepest truth may be about wonder. The expanding universe is strange, counterintuitive, filled with mysteries. And yet we can ask questions about it, gather evidence, build models, reach conclusions. The fact that we, tiny beings on a small planet, can comprehend something as vast as cosmic expansion is itself a kind of miracle. The deepest truth is that consciousness, the ability to wonder and understand, is one of the most remarkable phenomena in the universe. As you let this settle, imagine standing at the edge of all knowledge, looking out at the mysteries still unsolved. The expanding universe has revealed much, but it has also shown us how much remains hidden. The deepest truth is not a single fact, but a tapestry of realizations, each strand connecting to the others, weaving a picture of a cosmos that is dynamic, mysterious, and endlessly fascinating. When the observations are complete, when the data are analyzed, when the models are refined, there comes a moment to pause and ask, what does it all mean? The expanding universe is a scientific fact, confirmed by evidence and understood through mathematics. But it is also something more. It is a revelation that touches on the deepest questions of existence, purpose, and our place in the cosmos. One meaning of the expansion is that the universe has a story. It is not eternal and unchanging, but evolving. It began in a hot, dense state and has been cooling and spreading ever since. This gives the cosmos a narrative arc, a beginning, a middle, and perhaps an end. We live in the middle, in an era when stars still shine, when galaxies cluster, when structure and complexity are possible. To ponder this is to see our moment as fleeting, a brief chapter in a much longer book. Another meaning is that we are not separate from the story. We are part of it. The atoms in our bodies were forged in the cores of stars that lived and died before the Earth existed. The expansion of space determined how galaxies formed, how stars ignited, how planets coalesced. Without the expansion, without the precise rate at which space stretched, conditions would have been different. Have formed, stars might not have created the elements necessary for life. The expansion is not just background, it is the context in which everything, including us, arose. To ponder the meaning is also to confront the question of purpose. Does the universe have a purpose? Does the expansion serve some goal? Science does not answer these questions because science deals with how, not why. It describes the mechanisms, the laws, the patterns, but it does not tell us whether there is intention behind them. Some find purpose in the beauty and order of the cosmos, in the fact that it is knowable. Others accept that purpose may be absent, that the universe simply is, without needing a reason. What the expansion does reveal is that if there is purpose, it is not centered on us. The cosmos does not revolve around humanity. It existed for billions of years before we appeared, and it will continue for trillions more after we are gone. Our significance, if we have any, is not given by the universe. It is something we create through our actions, our relationships, our quest for understanding. To ponder the meaning is to accept responsibility for making meaning. There is also the question of fate. If the universe is expanding and accelerating, what does that imply for the future? If dark energy continues to dominate, the cosmos will grow colder, emptier, darker, stars will exhaust their fuel, galaxies will drift beyond reach, and eventually, even black holes will evaporate. The universe will end not in fire, but in silence. This vision is stark, but it is also honest. To ponder it is to accept that nothing lasts forever, that even the cosmos has a lifespan. Yet this fate is so distant, measured in trillions of years, that it does not touch the immediate concerns of life. The stars will shine for eons. The sun will warm the earth for billions more years. There is time, vast stretches of it, for life to evolve, for civilizations to rise, for discoveries to be made. The ultimate fate of the universe is not a reason for despair. It is a reminder of impermanence, a call to appreciate the present. To ponder the meaning of expansion is also to reflect on limits. There are horizons beyond which we cannot see, mysteries we may never solve. The universe contains regions forever cut off from us by the speed of light and the stretching of space. To know this is to recognize that knowledge is finite, that there are questions without answers. And yet, within those limits, there is so much to explore, so much to understand. The meaning is not in knowing everything, but in the pursuit of knowing. The expansion also suggests that reality is larger than perception. We see galaxies, stars, planets, but most of the universe is invisible to us. Dark matter, dark energy, the vast regions beyond our horizon, all exist but remain hidden. To ponder this is to acknowledge that the universe does not reveal itself completely. that mystery is built into the structure of things. And perhaps that is part of the meaning, that there will always be more to discover, always deeper layers to uncover. Another layer of meaning comes from the connection between the very large and the very small. The expansion of the universe is influenced by quantum fluctuations that occurred in the first moments after the Big Bang. These tiny ripples in the fabric of space-time, stretched by inflation, became the seeds of galaxies. The meaning is that scale matters, but also that scales are connected. What happens at the smallest level influences the largest, and vice versa. The universe is a unified system, not a collection of separate parts. To ponder the meaning is also to consider the role of consciousness. We are, as far as we know, the universe becoming aware of itself. Through human eyes, the cosmos observes its own structure, measures its own expansion, contemplates its own fate. This is remarkable. It suggests that consciousness, however brief and localized, is a significant phenomenon. The meaning may be that awareness itself is valuable, that the act of understanding is worth something, even in a universe that does not care. There is a poignancy in pondering the meaning. The universe is indifferent. It does not love us, does not watch over us, does not care whether we understand it. And yet we care. We ask questions, seek answers, build telescopes, write equations, look up at the stars with wonder. The meaning may be in that act of caring, in the refusal to accept ignorance, in the determination to make sense of things, even when the cosmos offers no guarantees. As you rest now, let the meaning settle. The expanding universe is not just a fact to be memorized. It is an invitation to reflect, to ponder, to ask what it all signifies. But the questions themselves have value. They connect us to something larger, remind us of our place, and give us direction. Every story has an ending, but some endings are also beginnings. The story of the expanding universe, of horizons and mysteries, of dreamers and discoveries, does not truly end. It continues, carried forward by each generation, each question, each observer who looks up at the night sky and wonders. The legacy of this knowledge is not just in what we have learned, but in how it shapes what comes next. The legacy lives in the observatories that dot the earth, perched on mountaintops, tucked into deserts, orbiting in space. Each one is a testament to human curiosity, a monument to the desire to understand. The telescopes built today will gather light for decades, adding to the great archive of cosmic knowledge. Future astronomers will use that data, build on it, refine it, discover things we cannot yet imagine. The legacy is continuity, the passing of knowledge from one generation to the next. The legacy also lives in education, in classrooms where students learn about the Big Bang, the red shift, the acceleration. These ideas, once known only to a handful of specialists, are now part of the common understanding. Children grow up knowing that the universe is expanding, that it had a beginning, that we live on a small planet in a vast cosmos. This knowledge shapes how they see themselves, how they think about their place in the world. The legacy is awareness, the spreading of cosmic perspective. The legacy lives in the questions that remain unanswered. What is dark energy? What is dark matter? Are there other universes? What happened before the Big Bang, if that question even makes sense? These mysteries are the inheritance of future scientists, the challenges they will tackle with new instruments and new ideas. The legacy is not closure, but openness, the recognition that there is always more to learn. The story also loops back to where it began, to the quiet wonder of looking up at the stars. Every discovery, every equation, every measurement starts with that simple act. Someone looks upward, sees something they do not understand, and asks a question. That is how Edwin Hubble began. That is how George Lemaitre began. That is how every great discovery begins. The legacy is the continuity of wonder, the thread that connects ancient stargazers to modern cosmologists. To look at the night sky now, knowing what we know, is to see it differently. The stars are not fixed points, but participants in a grand unfolding. The galaxies are not static islands, but travellers, carried by the stretching of space. The faint glow of the Milky Way is not eternal, but temporary, a structure that will one day disperse. The legacy is this transformed vision, this ability to see time and motion and change written in the light above. The legacy also lives in the way we think about endings. The universe will not last forever in its current form. The stars will fade, the galaxies will scatter, the cosmos will grow cold. But that distant fate does not diminish the present. It enriches it, adds urgency and beauty to the time we have. The legacy is the recognition that impermanence is not a flaw, but a feature, that the fleeting nature of things makes them precious. There is also a legacy of humility. The expanding universe has shown us that we are not the center, not the purpose, not the point. We are one species on one planet, in one galaxy, among billions. This could be diminishing, but it is also freeing. It means we do not carry the weight of cosmic significance. We are free to make our own meaning, to find our own purpose, to live our lives without needing the universe's approval. The legacy is the liberation that comes from accepting our smallness. The story loops back to the people who made it possible, the dreamers, the observers, the theorists, the engineers. Their names are remembered in observatories, in equations, in the histories we tell. But their true legacy is not in monuments. It is in the knowledge they created, the doors they opened, the questions they inspired. Every time someone looks through a telescope, measures a red shift, or contemplates the fate of the cosmos, they walk in the footsteps of those who came before. The legacy is continuity across time. As the universe expands, as galaxies recede, as stars burn and fade, the story continues. New observers will arise, new questions will be asked, new discoveries will be made. The legacy of the expanding universe is not fixed. It is alive, evolving, unfolding, just as the cosmos itself unfolds. Each generation adds its chapter, its observations, its insights, and the story grows richer. The return is to the beginning, to the simple act of wonder. After all the science, all the mathematics, all the philosophy, there remains the night sky. It is still there, still vast, still beautiful. The stars still shine, though we now know they are fleeting. The galaxies still glow, though we know they are receding. The cosmos still invites us to look, to ask, to wonder. This is where the story rests, not in a final answer, but in a return to curiosity. The expanding universe is not a puzzle to be solved once and forgotten. It is an ongoing conversation, a relationship between humanity and the cosmos. The legacy is that conversation, carried forward by every person who pauses to look upward and asks, what lies beyond? As you let your eyes close, as sleep approaches, picture the night sky one last time. The stars are drifting, the galaxies receding, the universe expanding. But here, now, in this moment, you can rest. The cosmos is vast, but you are part of it. The story is long, but you are in it. The legacy continues, and so does the wonder. The journey through the expanding universe has brought us full circle, from the first observation of motion to the deepest questions of meaning. And now, as the night deepens, The story becomes a lullaby. The galaxies drift outward, carrying their light into the dark. The expansion continues, silent and steady. And you, resting here, are, connected to it all, a brief spark of consciousness in a cosmos that stretches beyond comprehension. The legacy is yours now, the wonder is yours, and the stars, distant and ancient, shine on.